Okay, good morning. Welcome to the class. Today, let's have a look at the sixth lesson of chapter 5. Today, we're going to talk about Cartesian vectors and their operations in 3 space. So force, velocity, and other vector quantities often involve a third dimension. How can we plot 3-dimensional points and vectors in 2 dimensions? In this lesson, we will develop and use a Cartesian system to represent 3D points and vectors. We will also extend operations used on 2D vectors to 3D vectors. Note that 2D means 2-dimensional or 2 dimensions. 2 space is another short for 2-dimensional space, whereas 3D means 3-dimensional, 3 dimensions, and 3 space is short for 3-dimensional space. Okay, first, let's have a look at today's learning goals. After this lesson, you are expected to be able to develop a 3D coordinate system, understand the concepts of Cartesian vector, position vector, and unit vector in 3 space. Determine the magnitude and direction of a Cartesian vector in 3 space. Apply operations on vectors such as addition, subtraction, scalar multiplication, dot product, and projection in 3 space. Then determine the Cartesian vector between 2 points in the form of position vector in 3 space. Last, use Cartesian vectors to solve related problems in 3 space. Okay, first, let's develop a 3D coordinate system. It can be challenged to draw a 3D graph on a 2D piece of paper. By convention, we set the X, Y, and Z axis as shown here on the right. The negative axes are shown with broken lines. This is called a right-handed system. That means if you curl your fingers of your right hand from the positive X-axis to the positive Y-axis, your thumb will point in the direction of the positive Z-axis. You understand? Okay, I'll give you 1 minute to have a look at this, okay? Do you have any questions here? This is how we can set up a 3 coordinate system. Okay, so in the 3 system we have just set up, to plot the point 2, -3, 7, start at the origin, move 2 units along the positive x-axis, then 3 units parallel to the negative y-axis, and then 7 units parallel to the positive z-axis. then we get the point. It is often a good idea to plot the coordinates of 3D points by drawing line segments illustrating their coordinate positions, as shown here on the figure on the right. A 2D Cartesian graph has 4 quadrants. A 3D graph has 8 octants. The first octant has points with 3 positive coordinates. There is no agreement on how the other 7 octants should be named. Okay, do you have any questions here? All right, if no questions, let's have a look at a practice. Can you plot the points A, B, C, and D here, whose coordinates are given to you? Also, describe the location of each point. Okay, I'll give you 4 minutes to have a look at this example question. Try to do this by yourself, and then we'll have a look at the solution together, okay? Okay, have you finished? Okay, let's have a look at the solution together. Well, this actually trains your imagination in the three-dimensional space. We can plot the 4 points like this, as shown here in the 4 graphs. So note that point A is in the octant that is to the front right top of the origin, where all 3 coordinates are positive. And point B, this is point B, right? So I should put it here. This is point B, and point A. Point B is on the negative z-axis, which is here. So point C is here. Point C is on the xy plane, which means its z coordinates is 0, right? And point D is in the octant that is to the back left top of the origin, where the x and y coordinates are negative and the z coordinate is positive. Okay, any questions? All right, if no questions, let's have a look at another concept, which is a position vector in 3D Cartesian. Position vector for 3D Cartesian vectors. So let vector V represent a vector in space. If vector V is translated so that its tail is at the origin O, then its tip will be at some point P with coordinates x1, y1, z1, right? Then vector V is the position vector of the point P. And vector V equals vector OP, which can be noted by this symbol. First, a square parenthesis. Inside square parentheses are the coordinates of P, which is x1, y1, z1. This is vector V or vector OP, okay? This is called the position vector. The vector x1, y1, z1, as shown here in this figure, the vector highlighted in blue also represents any vector that has the same magnitude and direction as OP. Okay, so have a look at this concept here. Do you have any questions? Right, if no questions, let's have a look at another concept, which is a unit vector. As in 2 dimensions, we define the unit vectors along the axis, right? The unit vector along the x-axis in 3 space is defined as I, which is 1, 0, 0. The unit vector along the y-axis is defined as J, which is 0, 1, 0. And the unit vector along the z-axis is K, which is 0, 0, 1. From the diagram, we know the definition of unit vectors. You can also see that vectors I, J, and K all have magnitude or length 1. So these are the unit vectors in 3 space. As with 2D vectors, 3D vectors can be written as the sum of multiples of I, j, and k, the 3 unit vectors in the 3 directions, x, y, and z direction, right? Consider a vector u, which is a, b, c. Since the position vector OP of u, where the coordinates of p are a, b, and c, has the same magnitude and direction as u, we can use the vector OP to determine the characteristics of u. Vectors in 3D are added in the same way as vectors in 2D. By placing the tail of the second vector at the tip of the first vector. From the diagram, we know vector u is equivalent to vector OP, right? And vector OP is OQ plus vector QR plus vector RS, which is given by A. A is a real number, right? A, B, C are real numbers. A times vector I plus B times vector J times plus C times vector K, where I, J, K are the 3 unit vectors in the directions X, Y, Z. So that is given by A00 plus 0B0 plus 00C, right? Also from the previous page, we know vector U equals A, B, C. Thus, we have the following relationship. Any vector A, B, C equals A00 plus 0B0 plus 00C. So basically, the 3 components. Also equals A times the unit vector I plus B times the unit vector J plus C times the unit vector K. 3 components times the 3 unit vectors in the 3 directions, X, Y, and J, X, Y, and Z, respectively, right? Okay, any questions? Okay, no questions. Next, let's have a look at the magnitude of a Cartesian vector. So let's consider a vector u, which is equivalent to vector OP, which is A, B, C. To find the magnitude of u, we can use Pythagorean theorem in triangle OQR in the figure shown on the left. To find the magnitude of QR squared first. Since angle OQR is a right angle, we have the following relationship. The magnitude of OR squared equals the magnitude of OQ squared plus the magnitude of QR squared, which equals A squared plus B squared, right? Then we can use Pythagorean theorem in triangle ORP to find the magnitude of OP squared. Again, since angle ORP is a right triangle, we have the following relationship. The magnitude of U squared equals magnitude of OP squared, which equals the magnitude of OR squared plus the magnitude of RP squared. Then put all the values in. Note that we have already get the sum of the 2 magnitudes squared, right? Which is A squared plus B squared. Put all the values in here. A squared plus B squared. Then plus C squared. C squared is RP, magnitude of RP squared, right? And this gives us the magnitude of U squared equals A squared plus B squared plus C squared. Therefore, we have the magnitude of vector U equals the square root of A squared plus B squared plus C squared. A, B, C are the 3 components of vector u along the three directions: x direction, y direction, and z direction. Okay, so have a look at this. Any questions? Okay, if you don't have any questions, let's do a practice. For each vector below, first, sketch the position vector. Then write the vector in the form a I plus bj plus ck. I, j, k are the three unit vectors along the three directions. Then find the magnitude. Okay, question A, u is given by 3, -1, 2. Question B, another vector v is given by -2, 0, and 1. Okay, I'll give you 5 minutes to have a look at this question by yourself first. Okay, have you finished? Let's have a look at the solution together. So let's have a look at the question A first, which is illustrated in the graph on the left. So this vector U3, -1, 2 are the three components of U, right? This can be expressed as 3i minus j plus 2k. And the magnitude of U is given by square root of 3 square plus -1 square plus 2 square, which is square root of 14. Okay, question B, which is illustrated on the right. Vector V can be expressed as -2i plus 0j plus 1k, which is simplified to -2i plus k. Then the magnitude of V is given by square root of -2 square plus 0 square plus 1 square, which is square root of 5. Okay, any questions? Okay, if no questions, let's have a look at another concept, which is called the scalar multiplication in 3D. So for any vector U, which is U1, U2, U3, as the three components, and any scalar K belongs to the real number set, KU equals KU1, KU2, KU3. KU1, KU2, KU3 are the three components for K times vector U. As with 2D vectors, KU is collinear with U. This means that if you translate KU so that U and KU are tail to tail, then the two vectors lie on the same straight line. So here, I'm not going to show the proof of this property. You can try to prove this after this lesson by yourself, okay? All right, so if we have this rule for scalar multiplication in 3D, then let's consider an example here. Find A such that 1, 2, 3, this is a vector, and another vector, 2a6, are collinear. Question B, find a number B and C such that -2, B7, and C6, 21 are collinear. Okay, I'll give you 5 minutes to consider this question by yourself first. Okay, have you finished? Let's have a look at the solution together. Question 1, for vector 1, 2, 3, and 2a6 to be collinear. 2a6 must be a scalar multiple of 1, 2, 3, right? Looking at components of the two vectors, it appears that 2a6 is 2 times of 1, 2, 3. So we know a should be 2 times 2 or 4. In question B, we can let k represent the scalar. Then these two vectors are collinear is equivalent to C621, can be expressed as k times -2 b7. Therefore, we know C621 equals 2k, bk, 7k. So the corresponding component should be equal. So C equals -2k, 6 equals bk, 27 equals 7k. So from the third equation, we know k equals 3. Thus, C equals -6 and B equals 2, right? Okay, any questions? So note here, many of the tools we develop for 2D vectors can be easily modified for 3D vectors. Okay, so next let's have a look at the vector addition and subtraction in 3D. The 3D vectors can be combined to determine the resultants in a similar way to 2D vectors. For example, air traffic controllers need to consider ground speed, takeoff angle, and crosswinds while planning a takeoff. Vectors in 3 space have an additional component z, but the properties of vector addition and subtraction and dot product and other operations that were developed for 2 space are still valid in 3 space, as we can see here. So first, let's have a look at the vector addition in 3D. For two vectors u1, u2, u3, and vector v, v1, v2, v3. The addition of these two vectors, u plus v, is given by u1 plus v1, u2 plus v2, and u3 plus v3. And similarly, if u is u1, u2, u3, and v is v1, v2, v3, then u minus v is given by u1 minus v1, u2 minus v2, and u3 minus v3. Any questions? Okay, if no questions, let's have a look at next. The vectors between 2 points in 3D. So first, the vector between 2 points. The vector p1, p2 from point 1, whose coordinates are x1, y1, z1, to point p2, whose coordinates are x2, y2, z2, is vector p1, p2 equals x2 minus x1, y2 1 minus y1, and z2 minus z1. These are the 3 components of the vector p1, p2, a vector between the 2 points. So basically, we use the coordinates of the endpoint minus the coordinates of the starting point, right? Okay. Next, let's have a look at the magnitude of the vector between 2 points. The magnitude of the vector p1, p2 between the 2 points, p1, whose coordinates are x1, y1, z1, and p2, whose coordinates are x2, y2, z2, is given by the square root of the difference of x2 minus x1 squared plus the difference between y2 minus y1 squared plus the difference between z2 minus z1 squared. Okay, any questions? All right, if no questions, let's consider the following example. A, given the points A, 3, 6, -1, and the point B, -1, 0, 5, express vector AB as a ordered triple. Then write vector AB in terms of the unit vectors I, J, and K. Question B, determine the magnitude of vector AB. And question C, determine a unit vector U in the direction of vector AB. Okay, I'll give you 5 minutes to have a look at this question by yourself. Okay, have you finished? Let's have a look at the solution together. Okay, question A, the vector AB can be given by -1 minus 3, 0 minus 6, and 5 minus -1. So that's the three components are -4, -6, and 6, which can also be expressed as -4i minus 6j plus 6k. And the magnitude of vector AB is given by square root of the x component squared y component plus squared z component, which is square root of 88. Okay, question C from example on our textbook page 380. If you have the textbook, you can have a look at that. Unit vector in the direction of vector AB is 1 over the magnitude of the vector AB times vector AB. Then let U represent the unit vector in this case. You have unit vector U equals 1 over the magnitude of vector AB times the vector AB itself, which is 1 over square root of 88 times the vector -4, -6, and 6. Then this can be simplified to -2 over square root of 22, -3 over square root of 22, and 3 over square root of 22. All right, any questions? Okay, no questions. Let's have a look at another concept, which is the dot product for vectors in 3D. For two 3D Cartesian vectors, U, which is U1, U2, U3, and V, V1, V2, V3. The dot product between these two vectors is U1, V1 plus U2, V2 plus U3, V3. Note that we also have the following relationship in three-dimensional space. Dot product of U and V equals the magnitude of U times magnitude of V times cosine theta, where theta is the angle between the vector U and vector V. Also, we have the following relationship. Vector U and vector U are orthogonal, is equivalent to the dot product between these two vectors equals 0. Or two non-zero vectors A and B are orthogonal or perpendicular if and only if the dot product between these two vectors is 0. Okay, any questions? Okay, so next let's have a look at the properties of operations with Cartesian vectors in 3D. The properties of operations with Cartesian vectors in 3 space are actually the same as those in 2 space. Well, I'm not gonna prove all of these for you. You can use Cartesian vectors to prove these properties by yourself after this lesson, okay? So first, we have the commutative property, which means vector A plus vector B equals vector B plus vector A. For the dot product, we have dot product of A with B equals dot product of B with A. You can change the order of A, B, right? Next, we have the associative property, which means first, for addition and scalar multiplication, we can find the sum of we can apply the addition of vector A and B first, then plus vector C. This is equivalent to we find the sum of vector A and B and C first, then find vector A, the sum of vector A with the sum of vector B and C. You can change the order of the operations. For dot product, this is also applicable. A real number k times the dot product between A and B equals the real number k times A first, then dot product with vector B. Also, you can first calculate the scalar k times a vector B, and then find the dot product of A with the vector KB. Next, we have the distributive property, which means a scalar k times sum of vector A and B equals the scalar k times vector A plus the scalar k times vector B. And for the dot product between A and the sum of B and C equals dot product of A and B plus the dot product of A and C. Next, for the addition identity property. Any vector A plus a zero vector equals vector A itself. Next is the multiplication identity property. Real number 1 times a vector A equals vector A itself. And vector A times U, which is a unit vector in the same direction as vector A, equals unit vector U times vector A, which is actually the magnitude of A. So note here, vector A, B, and C are non-zero vectors, and K is a scalar, and K belongs to the real number set. Okay, again, you can use Cartesian vectors to prove these properties by yourself after this lesson. You can try this after this class, okay? Okay, next let's consider an example question. Given the vectors u, v, and w as shown here, simplify each vector expression. Okay, I'll give you 5 minutes to have a look at this question by yourself first. Okay, now let's have a look at the solution together. Question A, -3u is -3 times the vector u, which is 8, -4, 3, right? So final result is -24, 12, -9. That's the three components of the new vector. In question B, the sum of u, v, w. We can add the corresponding components. So x component is 2 plus 8 plus -6. Y component is 3 plus -4 plus -2. The component is -5 plus 3 plus 0. And that gives us 4, -3, -2. Okay, question C. We want to find the magnitude of u minus v. So first, let's find u minus v, the new vector, which is -6, 7, -8. And the magnitude of this vector is square root of -6 squared plus 7 squared plus -8 squared, which is a square root of 149. Okay, last one, the dot product of u and v. This is given by 2 by 8 plus 3 by -4 plus -5 by 3, which is -11. Okay, any questions? All right, if no questions, let's have a look at another example. Can you determine if the vectors A and B here are collinear or not? Okay, I'll give you 3 minutes to consider this problem by yourself first. Okay, have you finished? Okay, let's try to have a look at the solution together. Okay, note that if two vectors are collinear, is equivalent to one of the vectors can be expressed as k times another vector, right? So we can try to let vector A equals k times vector B. If there is a solution for k, then A and B should be collinear, right? So that's equivalent to where k belongs to the real number set. Therefore, we know 6 equals 9k, 2 equals 3k, 4 equals 6k. The three equalities must be satisfied at the same time, right? So the first one gives us k equals 2 over 3. The second one also gives us k equals 2 over 3. Third one also gives us k equals 2 over 3, right? Therefore, there does exist the solution k equals 2 over 3, such that A equals 2 over 3 times B. Therefore, A and B are collinear, right? So this is a possible method. Another possible method is to find the angle between these two vectors. Two vectors are collinear is also equivalent to the angle between these two vectors is 0, right? So how do we find the angle between the two vectors? We can use the dot product of these two vectors, right? So next, let's have a look at the second method. We can find the angle between the vectors using the dot product definition. Suppose theta is the angle between the two vectors. We have the following relationship. Cosine theta equals the dot product of A and B over the magnitude of A times the magnitude of B. Then substitute all the values in. We have 84 over the square root of 7056, which is actually 1. Therefore, we know theta equals arc cosine 1, which is 0 degrees. Therefore, we know vectors A and B are collinear. Okay, any questions? You can choose either method you like, okay? Any questions? Okay, if no questions, let's consider another example. Find a vector that is orthogonal to this vector, 3, 4, 5. Okay, again, I'll give you 5 minutes to have a look at this question. Okay, have you finished? Let's have a look at the solution together. So we can let x, y, z be the vector that is be a vector that is orthogonal to 3, 4, 5, right? Two vectors are orthogonal is equivalent to the dot product of these two vectors is 0. Therefore, we have 3x plus 4y plus 4z equals 0. Note that in 3 space, an infinite number of vectors can be orthogonal to 3, 4, 5, right? We can then select any values that satisfy this equation. We can simply let x equals 2 and y equals 1, then solve z equals -2. Therefore, we can find a vector 2, 1, -2, which is orthogonal to 3, 4, 5. Okay, any questions? No questions? Let's consider another example. A crane lifts a steel beam upward with a force of 5,000 newtons. At the same time, two workers push the beam with a force of 600 newtons towards the west and 650 newtons towards north. Determine the magnitude of the resultant force acting on the beam. Okay, I'll give you 2 minutes to quickly have a look at this question. Okay, now you should be able to finish this question. So let's have a look at the solution together. So note that the three forces are perpendicular to each other, right? Define the vertical vector as 0, 0, 5,000. That's from the crane. Then the other two vectors are horizontal. We can define the force to the west as -600, 0, 0, and the force to the north as 0, 650, 0. So the resultant force R is given by the sum of the three vectors, right? And then substitute all the values in. This gives us -600, 650, and 5,000. Then the magnitude of R is given by the square root of the squared components, respectively. So that gives us approximately 5077.6 newtons. So the magnitude of the resultant force is about 5078 newtons. Okay, any questions? Okay, if no questions, let's consider another example. Again, this is an application problem, involves vectors in 3 space. A force with units in newtons and defined by F, 300, 700, 500, acts on a object with displacement in meters defined by D, 3, 1, 12. A, determine the work done in the direction of travel. B, determine the work done against gravity, which is a force in the direction of the -z axis. Okay, I'll give you 4 minutes to have a look at the solution of this question, and then we'll have a look at this question together. Okay, now let's have a look at the solution together. Remember, in the two-dimensional space, the work done by a force is given by W equals the dot product of the force F times the displacement S, right? Which is given by its magnitude F times the magnitude of S times cosine theta. Theta is the angle between F and S. So this is also applicable in the three-dimensional space. So put all the values in. The magnitude of F is, F is 300, 700, and 500. These are the three components, right? So this is F, and the S is given by 3, 1, 12, and unit is meters. So the dot product between these two vectors is 300 times 3 plus 700 times 1 plus 500 times 12, which is 7,600. So the work performed in the direction of travel is 7,600 joules. In question B, since the work is to be calculated against gravity, we must use only the vertical components of F and S, right? Which are 0,0500 and 0,012, respectively. Therefore, the work done is dot product between these two vectors, which is 0 times 0 plus 0 times 0 plus 500 times 12, which is 6,000. So the work performed against gravity is 6,000 joules. Okay, any questions? Okay, if no questions, let's have a look at the last concept in today's lesson, which is vector projections in three-dimensional case. So the projections in 3D are similar to those in 2D, so we can use the same formula. Remember, when we talk about the vector projections in 2D, we have the following relationship. So this is also applicable in 3D case. The projection of vector v on vector u, where theta is the angle between v and u, is given by the following formula. Projection of v on u is the magnitude of v times cosine theta times 1 over the magnitude of vector u, then times vector u. Or this can also be given by the projection of vector v on u is the dot product between v and u over the dot product between u with u itself, then times the vector u. Also note that if theta is between 0 and 90 degrees, the magnitude of the projection is the magnitude of v times cosine theta, or the dot product of u and v over the magnitude of u. Whereas if theta is between 90 and 180 degrees, then you should put a negative symbol in front of the right side for each of the two formulas. Okay, I'll give you 3 minutes to have a look at the formulas here. And we're going to have a look at one last example, which is about vector projection in 3D space. Okay, so let's use this concept to solve a problem like this. Can you determine the projection and its magnitude of vector v, which is given by 4, 2, 7, on another vector u, which is given by 6, 3, 8? Okay, I'll give you 5 minutes to consider this problem by yourself. Okay, have you finished? Let's have a look at the solution. So note here, the angle between these two vectors are not directly given to us, right? But we know the three components for both of the two vectors. So it's better to use the second formula here. This one. So the projection of V on U is calculated using the dot product of V and U over the dot product of U with itself. So put all the values in, we can find that's actually 86 over 109, right? Do not forget that followed by a vector U here, because the projection is a vector, not a scalar. Do not forget there is a U behind. So 86 over 109 times the vector 638. Of course, you can also put this number in the three components. Or you can just leave it there because we want to find its magnitude anyway. Since the magnitude of this projection is the magnitude of the vector you obtained here. Again, put all the values in. That gives us 86 over 109 times the magnitude of this vector, 638. And that gives us 86 over 109 times the square root of 6 squared plus 3 squared plus 8 squared. And that's approximately 8.2. Okay, have a look at this question here. Do you have any questions? Okay, let's have a look at today's learning goals again. So after this lesson, now you should be able to develop a 3D coordinate system, understand the concept of Cartesian vector, position vector, and unit vector in the 3 space settings. Determine the magnitude and direction of a Cartesian vector in 3 space. Then apply operations on vectors such as addition, subtraction, scalar multiplication, and dot product in 3 space. Next, determine the Cartesian vector between 2 points in the form of a position vector in 3 space. And last, use Cartesian vectors to solve related problems in 3 space. Okay, so that's the end of today's class. Let's dismiss for today, and I'll see you next time.